Today we'll talk about a new algorithm called particle swarm optimization. To set this up, let's imagine the scenario where you get a big group of your friends and there's this field, let's say, and you're trying to find something in this field. So this big grass field, and you need to search this space for something. And I guess to make it more like an optimization problem, let's pretend that on the field, this is a bit contrived, obviously. There are tons of these little tiny numbers around these little pieces of paper. Um, and you're trying to find the minimum value here. How would you do this? What kind of strategy would you use? Well, you'd probably imagine that since you have a group of friends, you're going to spread out, right? You're not all going to search in the same space. You're going to kind of spread out. And you'll also communicate. As you find good places, you're going to maybe share that information. And if there's an area that's really promising, maybe more of you will gather there. But even while others are gathering, you may still want to have others that are searching. This is more or less the way that the particle swarm method works. It's biologically inspired. You could think of a swarm of bees, maybe squirrels, birds, any number of biological examples where we can have these swarm, a group of agents, we'll call it. I'm sharing my screen right now, that's why it's gonna look weird. That are trying to explore the space, and each of them, is just doing a very simple job, but by coordinating and talking together, you can, do much better by sharing information. Okay, so this is particle swarm optimization. I'm going to walk through the main ideas here. So to begin with, let's discuss the main concepts, and there are really three that are used here. Okay, the first is inertia. Okay, and inertia just means that, and we'll call each of these, I guess we've been calling them particles. In particle swarm, call them agent. I'll call them a particle, I guess. A particle will tend to head in the same direction it was headed. Okay, so all that means is that it's not going to be erratic. We're not just going to randomly jump all over the place. That's going to be hard to really explore. If you were exploring this place too, you'd probably have some direction. That doesn't mean that direction can't change, but it's not going to be totally erratic. If you're going one way, there's going to be some tendency to go that way. Okay, and these are going to be three sort of competing criteria. The second is going to be memory. Okay, so you're going to remember where you've been, and as you're searching the space, you may find, wow, the values here are getting way worse. Maybe I should go back to that place I was at where things were better. That's kind of the idea in the memory sense, is that each particle, remembers best place it has seen and will tend to return. Okay, that doesn't mean every step you want to just go back, right? Just because you saw something good, but as you explore, there's going to be some tendency to go back to the best place you found so far, because it's likely, right? Because remember, this is a continuous space, that just because you saw something good, that's probably not the best that was in that area. There might be better places nearby. And the last is this social aspect that we kind of were talking about, which is this idea that we want to share information. And so a particle will want to visit best place that the swarm has seen. Okay, so that was that idea of communicating, and if someone says, oh, there's some really great stuff over here, you're going to want to tend to go there. Maybe not everyone, maybe it will really vary, but there's going to be some tendency to want to go there. So the difference between these two is, this is the best I've seen, this is the best the group has seen. All right, so the idea is that at every step, a particle is going to move based on some combination of these three criteria. So let's say here's where I was at, and this is my inertia. This is where I was going. Okay, so there's going to be some component that's going to want to continue that way. Let's say here, this is my, we'll call this the individual best. This is the best I've seen. And let's say maybe over here, this is the swarm best. Okay, and we'll talk a little bit about how to size these, but let's say there's some component, there's something drawing me that way, and there's something drawing me that way, right, where these lines are pointing towards these best ones. And so what I'm going to do is I'm actually going to take, my step is going to be the sum of these. So let's say I take this one here, plus let's take this, well, we'll just use this one next. That's going to look like that, right? And then I'll add this one. So I'm just taking the vector sum of all three of these. Looks something like that, let's say, just trying to draw it parallel. Okay, and then, so my total step at that next iteration is going to be the vector sum. So in other words, I'm influenced by all three. I'm influenced by inertia, by this memory, by social aspects, and my next step is going to be some combination of those influences, and then I'll repeat that process again. And there's going to be some randomness here. So sometimes maybe inertia is going to be stronger, sometimes the social aspect will be stronger. We'll see what that looks like in a second. All right, so that's the idea. Let's get a little bit into some of the math here. I thought I had some headers here, but it looks like I got rid of them, so I can write that. Inertia was the first idea, and mathematically we could write it this way. We could say that my velocity at the next iteration is going to be some multiplier times my velocity at the last iteration. And I'm going to repeat this for every agent in the swarm. So I is the ith particle. W here, this is called the inertial parameter. That is going to be some sort of weight that we choose and may change throughout the optimization, but it's going to affect how much the inertia term is going to dominate. And typically, the inertia term is somewhere near 1, right? Not too far off of 1. So I'm going to tend to want to go into the same direction. So the question for you then is, what is the effect of W? If I make W bigger or smaller, how do you think that's going to affect my optimization? Well, imagine that W is really large. That means my velocity is going to be increasing. I'm going to be increasing velocity, from each iteration more and more. That's going to encourage exploration. I'm going to be going all over the place. If W is decreasing, is small, then I'm going to tend to have smaller steps, and that's going to encourage exploitation, converging faster. So it's kind of a trade-off of converging a little bit faster, being more efficient, versus maybe being more robust in the sense that I'm going to keep exploring more. I'm not going to slow down as soon. And I'll mention this later, but most practical algorithms want to have some sort of velocity dampening, meaning this W term should decrease over time. And the idea is that maybe early we want to explore, but we don't want to keep going all over the place the whole time. We want to kind of start to slow it down, usually, right? That's an option. Okay, so that's inertia. Memory, it's the next one we talked about. And remember, that was just the idea that I want to go back towards the best I've found. So we could say my velocity of the individual particle at the k+1, it's going to be related to where I'm at, my x position, relative to the best I've found. So here's the best, and this is the best I've found. So there's a little I because it's particle I. And then this is the difference between where I am at my current iteration. So x is my position of particle I at iteration k, right? So this term is going to become bigger when I'm further away from the best I've seen. And so we're going to divide by this delta t to make it a velocity. We'll see this delta t is really just an artificial thing. It doesn't play any role. It'll cancel out, in other words. So I'm going to add one other term first, but let's just describe it this way, right? Look at the velocity like this. So what this means is that if I'm right at the best, then my memory term is going to do nothing. And if I'm close to it, there's going to be a small pull, right? But if I'm far away, this term is going to become potentially increasingly is going to become bigger, right? It's going to want to cause me to go back towards the best I've gone. I don't want to stray too far away from the best that I've found. So to make this, more like a biological system here, or maybe more robust in a sense, we're going to add this random number, C1. And so this is a random number, so we're going to draw a different number every time. And it's typically, let's say, around 2, the typical value. And you could do a different weighting C for every particle, but we don't have to. It could also be the same for the entire swarm. And so this is going to be a number. Actually, I shouldn't say it's not around 2, because of course it's going to be between 0 and 2 about. Okay, so we're going to draw a random number from a uniform sample. And it could be that, I draw a 0 or something close to 0. And even though I'm very far away, right, the memory term isn't going to contribute much. I'm going to continue what I'm already doing. Okay, so that's the idea, is that we don't want to, just because I'm far away doesn't mean I want to go back right away. There's some probability that I will, but there's also some probability that I'll stay and explore. Okay, the social term is very similar. So I'm just going to write it out directly here. This is my velocity at that next step, or at least that's a component of it. It's going to be the best, and this is not, there's no I here because it's not my best, it's the best that the group has seen, minus my position divided by delta t, and then I have a different random number, C2. Okay, and C2 is also going to be in the range, say 0 to 2 approximately. So it's a random number. Again, this is random. Let's say uniform distribution, and we randomly draw a number. So the inertia term, that's generally fixed. I mean, like we said, it may decrease over time perhaps, but it's not random. But the social and memory components are. So in other words, I'm going to tend to do what I was doing, but with some random probability, I'm going to be drawn towards the best that the swarm has seen or the best that I've seen. Okay, so there will be some tendency over time, not necessarily immediately because of randomness, but some tendency over time to kind of group towards these better spots. And that makes sense because eventually I do want to do that. I do want to explore, but I also want to group, at least have some that are grouping towards the best, because again, this is a continuous space. So it's likely that near that best, there's actually even better points, right? Okay, so let's put all those together. My total velocity then is the sum of all three. So it's the inertia term. It's inertia. Then there's the memory term. Minus xk divided by delta t. And then there's a social term here. I should have wrote this out beforehand. It's a lot to write. Okay, so there's all three together. And what we're going to do at the end is we actually want to do a position. We're going to update a position, not a velocity. So my position at the next iteration, a particle I, is going to be my position from the previous iteration plus my velocity times some time. Okay, so when we multiply time through, we see it's all going to cancel out. These will cancel. And then this velocity times time is just going to give me my position at the last iteration. So this is the final update. My change in position, this velocity is going to be the change in position over change in time. At iteration, I'm just going to drop all the i's. You'll know they're there. I just don't want to write it all. Okay, it's going to be my position at the previous iteration times some weight plus C1 times the difference in this. I have to write the I because it's the best I've seen times my position at the last iteration plus a random number times the best that anyone has seen minus xk. Okay, so this is the final one. And we're going to update that for every particle. Every particle is going to draw different random numbers, and it's going to take a different step. And so they're going to move independently, but with some relationship between them, because we're at least sharing this thing best. And I should say there are some variations where the sharing doesn't happen globally. It may happen within a neighborhood, right? It'd be kind of analogous to a really huge field where only nearby people can hear me yell and say, hey, there's something good here. But that's an algorithmic option. And again, remember that W is a number close to 1, usually around 0.8 to 1.2, and these are both random numbers, separate for every particle at each time step, and typically between 0 and 2, or around 2. Okay, so to make these practical, there are a couple things that are usually done. One is called velocity clamping. And effectively, that just means that I should specify beforehand some maximum velocity, or in other words, some delta x. Probably easier to say it that way. You could think of it as a velocity clamping, but really it's a position change. A maximum delta x I'm going to go. I don't want it to get out of hand where the inertia term keeps growing too much and I'm like zipping all over the place. It's effectively going to become a random search if I just am hopping around so far, because then a point way far away is going to have no real relationship to where I'm at. So, maybe something like, say, 10% of the bounds might be a reasonable maximum, but some sort of limiting factor that we won't increase beyond. Another thing that I already mentioned that's often used is, it's called velocity damping. And that's the idea that, delta x max might decrease each iteration. So maybe I multiply by, say, I don't know, 0.9 or maybe something bigger. It depends how much I want to decrease it. Or alternatively, I could decrease the parameter W. But this is just going to help me, depending on my convergence criteria, but it may help encourage convergence eventually, so I don't just keep jumping around all over, because eventually I want them not to go too far, and that'll help them start to congregate and explore the more promising regions more finely. Because again, early on, I want them to explore and move around quite a bit. But eventually, I've kind of identified some promising regions, and I want things to kind of settle in a smaller area. So I want that maximum velocity to decrease. Okay, so how do we initialize? I mean, this is really going to be the same as the genetic algorithm. Could be random or pseudo-random stuff. I mean, a better random one would be like Latin hypercube sampling. I know I keep saying this and we haven't talked about it, but we will talk about it later. But again, the idea is that it's random. It's a random method, but it's going to use in a way that we spread points out well in an optimal sense. How do we converge? It could be like genetic algorithm where we just put a time budget, but there are other ways. These tend to converge a little more efficiently. So there may be things like, let's say, the best value is not changing too much. Could be that the velocity has decreased below some tolerance, or that the particles are all pretty close. That one we have to be careful with. It depends. Let's say I've got a multimodal problem, and that's usually when I like to use, when one might like to use methods like this. So let's say I've got a minimum over here, and there's another one over here. I've got some sort of search space. I may have a bunch of particles over here and some over here. So I may not want to actually compare the distance between all the particles, because they could still be very spread out. In that case, I might want to use a criteria like looking at the best value. But the best value, we want to make sure that it's not changing below some tolerance for a while. Okay, so those are some options that could be used. Here's a kind of picture of how this might look like. So this is kind of our modified bean function, we've been calling it, unconstrained problem. And so here you can see, like say, initial point where we've got all these particles, and actually have to initialize both the particles and a velocity. So here's the particle, their positions and a direction they're going, this velocity term. And then this is to show some discrete iterations. These are not one iteration, but several iterations later, it might look like this. And you'll notice they're actually not quite as spread out. This is maybe not the best illustration because it's unimodal. And then you can see they're going to start clustering more and really searching that space. And eventually they're very finely packed in there and have really explored it pretty well. Okay, just to end here, I'm going to do a quick demo. This is going to be illustrating this algorithm, but also the other two that we've recently talked about. I think I showed you one of them already, but let's see, I don't know that I have. Oh, actually, I'll just open up a new window here. I didn't get this quite ready to go, so just setting up real quick. Okay, now let me change my screen. Where is that? Just share my whole screen here. Okay, so there we go. This is going to do the Nelder-Mead, the genetic algorithm, and a particle swarm. These are just my version of these that I wrote. And we're going to look at how they look. I put some artificial pauses in here so we can see them, but they don't actually run this slowly, but just so we could watch and see what's happening. All right, so this one I think I already showed you, but just a recap here. This is the Nelder-Mead. Remember, this is the tetrahedron. And this method, again, it's going to work pretty well if you are looking for a local search, right? So it doesn't do the same kind of spreading and exploring as the other methods do, but it's generally more efficient than most of the other gradient-free methods if it works for your problem. It can converge to a better tolerance usually, especially compared to something like a genetic algorithm. So here's a genetic algorithm. Here's my initial points. You can see they're kind of all spread out. And then, through the selection, reproduction, and mutation, they're moving. And this one is going to be more efficient than the one I showed you, the MATLAB one. This implementation is more effective for this particular problem. It's getting pretty close to converge. Okay, it's done. There's a particle swarm. Here are the initial positions and velocities, and they're going to start moving around. They're exploring, they're exchanging information. And again, this one isn't quite as exciting because it's kind of unimodal. It's more interesting on a multimodal problem because you'll see them maybe searching different spaces. And they won't all converge on one spot even, because there's still some probability that some will be off exploring, and that's desirable, but they'll often start to converge. Okay, so those are the ones we've talked about. I think those are the main ones we're going to discuss. There are a couple more in the book that you might be interested in. There's a direct method. This one is a bit more, it's not a heuristic, it's mathematically derived. That can be an effective approach sometimes. There's another one, it's actually new. I just wrote about it this week, so you'd have to download the latest version of the book. But a pattern search method, this is also a popular approach that's effective for these multimodal problems, or can be effective for these multimodal problems. Let's see, actually, I wonder, I may have one handy. Let's see. What did I call it? Yeah. Maybe I can just show you real quick. Actually, you know what? I'm going to run it from the terminal because I'm doing it. I got a little plot in there. And I'm going to turn on this interactive. So again, I'm doing the same thing. I put some pauses in here so you could see what's happening. And the idea is that it does, it searches, it has two kind of steps. One is it's doing this exploration phase, and then it's got this local phase where it's going to look at places that are nearby. And you can choose these vectors in different ways, but they're going to be aligned with coordinates. It's going too fast. I'll just slow it down. But let me just show you what's going on real quick before I redo it. You can see there's some that are exploring, and then there are others that are like searching in kind of this pattern, and they're aligned with the coordinate directions in this example, but they don't have to be. Let me increase the pause here so we can just make this a little bit slower. Let's do like a second. All right, so again, like I said, there are two phases. There's this random search where it's going to like sort of explore the bigger space as that global search. But then it's going to do, if it doesn't find better ones globally, it goes to a local search, and it kind of goes back and forth depending on which ones are working well. So here it's doing that kind of grid pattern. And if it finds something better there, it'll take it. If not, kind of is going back. Here it's doing another grid, but it found a good one, so it moved on. Here's kind of a grid around that point. And as it does that grid, if it finds a good point, it'll immediately move on to the next one. So anyway, you can go read about some of the details there, but the idea is it's kind of combining those two levels. There's kind of this global exploration that happens and also sort of a local refinement. And now you notice that it's seeing there's good spots here, so it's going to spend a little more time doing local things, but occasionally still, right, it's going to jump out and do an exploration, but then it's going to come back here because it's more promising. There are a lot of variations of this. Maybe a more recent one is called MADS, which allows for more general directions than just these. It gives you more options. Anyway, so there are a lot of methods out in the gradient-free world, and we just talked about a few of the main ones, but just to give you some flavor, or some of the more popular ones, like I think genetic algorithms, particle swarm, pattern search, Nelder-Mead, those are some of the more well-known ones. And we've seen even amongst those, though, they can really vary in their characteristics. Some have a lot of randomness involved. Others are more deterministic. Actually, this this pattern search I was just showing you does have randomness as well. Others are more local, right? They're going to try to converge to a local one. They're going to be more efficient in that sense. Others are trying to search more globally. They may be slower, but they may be more robust in finding different options. Some use heuristics, right, where we're going to use things that are inspired off biology, especially often use heuristics. Others are going to use more mathematical criteria. So their range, and it helps to have options because it's hard to know necessarily beforehand which one is going to be best. Okay, so that's it for this segment. We're actually going to continue with some gradient-free problems, but in the context of discrete optimization. So I'm going to start discussing some techniques for problems where some of the variables are discrete. They take, integers or discrete values and not continuous variables. All right, see you next time.